Okay, Year 12, here's our first lesson for the next topic, which is Chapter 12, and it's investments, annuities, and loans, which is interesting because we actually start out with something that's not investments or money financial. It's this arithmetic growth and decay, as you can see, 12.01 and 12.02. Now, there are money aspects. You can relate money aspects to them, like straight line depreciation and straight line simple interest. And in the geometric one, exponential decay, the depreciation, and exponential investment. But if we look at the syllabus here and where these come in, so number M1.1 there, we're not starting with that. We will be. They're doing compound interest and using technology and interest. But here, where this exponential or arithmetic growth and decay, it comes in 1.2. You can see there, it's the last dot point. Identify and use arithmetic sequence and arithmetic series in contexts involving discrete linear growth or decay, such as simple interest or straight line depreciation. So if you've got, you buy a computer and you claim that on tax, and they depreciate that by 30%, a third every year. After 3 years, the value will be zero. And that's straight line depreciation. And you'll notice here that the geometric growth and decay comes actually into financial expert. It comes into M1.4. Use geometric sequences to model and analyze practical problems involving exponential growth and decay. So, where does that take us? So, there's some terminology there that we're going to get involved in. That won't come in until we get into exercises 203 and 204. So here's 1201, 1203 and 1204. Here's 1201, and we're talking here about growth, which is increase, and decay, which is decrease. And as you can see, we're talking about linear. So an example of a linear growth would be simple interest, which no one really uses. So you start, and here you have your money, and here you have time, and you start with an amount. Let's say you invested $10,000, and simple interest was a certain percentage. It was going up. That $10,000 would go up by the same amount each year. So let's say it was, I don't know, 10%, right? 10%. That means after 1 year, it had gone up $1,000. So 10,000, oops. And so on. It goes up by $1,000 every year because it's simple interest. The depreciation, straight line depreciation, and I'm using financial terms here. Let's say you bought a car or you bought a computer and it was worth $1,000 and you're depreciating that on tax, it would go in a straight line down until after. So let's say you depreciated 20% each year. So after the first year, the second year, the third year, oops, poor scale, 20%, no, the fourth year. Then after the fifth year, it'd be worth $0. The problem with depreciation as a straight line function is that after 6 years, your computer will be actually worth a negative amount. You need to make sure that you ignore negative values in straight line depreciation. So they're not very good models. No one really uses simple interest or well, you can use straight line depreciation for tax features, but very little else. So most of our examples in this arithmetic growth and decay are going to be things that are not financial. They might do some, but not many of them will be financial. So essentially, we're using our arithmetic series. So in those, and make sure that you know you have your formula sheet, and you know your formula sheet, and our arithmetic series is that one and that one. All right, these are geometric, so we're only using those two. So make sure you note those. So let's go back and go to year 12, and here we are. So let's write those two formulas down. So T of n equals A plus n minus 1 times D. And S of n equals, well, remember we've got two formulas, n on 2, is it 2A plus n minus 1 times D? Yep. Or, if you happen to know the last term, remember Carl Friedrich Gauss, n on 2, A plus L, where L is the last term. Excuse me. Righto. So, now, the other thing you need to be able to understand with these is you can play with these and get the answer without actually having to use those formulas. I'm going to show you how to do that, but if you do that in an exam, you must show all your working. Now, I'm not going to do all of these. There are quite a number of questions. I think there are 10. And I'm going to do a selection. But I'm going to do the first one to kick you off. And I'm going to do the first one in two ways. I'm going to do it intuitively using intuitive reasoning, although I won't be able to do this one intuitively. I'm going to have to use a formula. But A and B I can do. So here's A. And this gardener plants 44 bulbs in the first row, then 5 more, then 5 more, then 5 more. So what you could do, you go, so 45, 50, 55, and so on. And you could get your calculator out, and you go, right, I'm going up by 5. I start with 45, and then I add 5, and then I add 5, and I'm going to plant how many rows? 34 rows. And they're asking me how many bulbs are in the 34th row. So I'm thinking to myself, well, I'm going to go 45, and that's the first row, and then I'm going to add 33 more rows, because that's the first row, and they go up by 5. And I do that on my calculator, so I go 45 plus 33 times 5, 210. Now that's thinking about it intuitively, but what you actually have done is you've applied the formula. That's your A. Your D equals 5, 50, going up by 5. So T of n, T of 34, equals A, 45, plus n minus 1, 34 minus 1, times D, which is 5, and that's 210. So remember not to lose your intuitive ability or your mathematical skills. Now, what would be the first row to have more than 100 bulbs in it? Well, again, it's not going to take very long, is it? Like after 3 rows, remember this is the first row, this is the second row, this is the third row. It's not going to take very long to get up to the 100th. I mean, you could write them all out. So 60, 65, 70, 75, 80, 85. And some kids have done this, 90, 95. And it says more than 100, more than 100. So I have to go to 100 and 105. And I just go, 4, 5, 6, 7, 8, 9, 10, 11, 12. It'll be the 13th row. It'll be the 13th row. And hold on, I'm just getting my answers up. Hold on, have I lost it? Tell me I've lost it. There we go. It is the 13th row. But if I'm going to use this formula, so I'm going to go, T of n equals, well, if I find 100, or sorry, I want it to be greater than 100. I want it to be greater than 100. So I go, T of n is a plus n minus, so I want a plus n minus 1 times d is got to be greater than 100. A is 45. N minus 1 times 5, it's got to be greater than 100. Minus the 45, so you get n minus 1 times 5 equals 55. Divide the 5, so, oh, sorry, I've got equals there, it's got to be greater than. Therefore, m minus 1 is going to be greater. Divide the 55 is 11. Add the 1 over. M has got to be greater than 12, which means n will equal 13, sorry. Because that's the first term, greater than 100. Okay. Now, if you were to do that in exam and you were to write all that out, yep, full marks for that. Anyway, let's now have a look at C. Market gardener plants that many bulbs. How many rows are there? Well, I have to use this formula. So, C, S of n equals 10, 5, 4, 5. 10, 5, 4, 5. So 10, 5, 4, 5. And you can imagine trying to do this. It would take a long time if you tried to do this. So by hand, like you did above. And you've got to add every one. So we've got n on 2, because we're using this formula over here. See the one with the green highlight. 2a, so 2 times 45, plus n minus 1 times 5. Now, let's multiply that 2 across. So 10,545. I'm going to multiply the 2. So I get 21090 equals n 90 plus 5n minus 5. So I get 21090 equals n 5n minus plus 85. So now I'm going to get 21090 equals 5n squared plus 85n. And I'm going to write that as a quadratic. So I'm going to 5n squared plus 85n minus 21090 equals 0. I'm going to divide everything by 5. So I'm going to get n squared equals plus 17n minus, I'm going to have to do this one on my calculator, divided by 5. 4218. Now, trying to find two numbers that multiply out to negative 4218. One has to be positive and one has to be negative. That's going to be really hard. I'd play on my calculator. I don't know. Why don't I try... what do I have? 4218. 4218. Because I know they have to be a whole number. Divided by 32. That doesn't work out. And those two numbers are far apart. They've only got to be 17 apart. So I need a number bigger than 32. So 4218 divided by 43. Now they're closer together, but even still, not a whole number, so I have to go a bit higher. So you can see how I'm doing this. 4218 divided by 52. All right, they're less than 30 apart, so I'm getting closer. So 4218 divided by 56. Now, they're pretty close. I might try 57. 4218 divided by 57. Oh dear. 218 divided by, oh, come on, 57. 57 and 74. Okay. So let's try, what's 74 minus 57? 17. So they're my two numbers. So that would have been really hard. You could have gone straight to the quadratic equation for this. So n plus, what was it, 74, n minus 57 equals 0. So therefore, n equals negative 74, or n equals 57. Now, we can ignore the negative number of rows. You can't have a negative number. You should always write it though. Therefore, n equals 57, 57 rows. Now, I probably wouldn't have mucked around. I would have gone straight to the quadratic formula for that. The numbers are too big. As you can see, I got it reasonably quickly, but, you know, it was hard. So let's have a go at another one. So I'm going to do two more, and then I'm going to wait for your questions. I might do 4, and I might do 10, because I know 10 is going to give you trouble. So let's have a look at 4. Now, it's always a good thing to write out in numbers what's going on. Now, even though this starts at 1.8 and goes to 1.2, you can do that and have your common difference be a negative number. Or you can make this your A and make that your last one. And I think that'll work better. So I'm going to let A equal 1.2. Now, there are 61 pieces. Now, you can think about this intuitively. There are 61 pieces of wood. So 1, 2, 3, 61. Now, here you have to be careful. Remember that there's going to be n minus 1 differences between them. There's going to be n minus 1. So the last term, so you don't know the common difference. The common difference is what you've got to find first. What is the difference in height between each pole? Now, sometimes this can be hard. So imagine if you only had 3. Imagine if you only had 3. So you have 1.2, you have one more there, and one more there. You've only got 2 differences. You've only got 2 differences. So you've got 61 pieces of timber. So you've got 60 differences. Now this is thinking about it intuitively. So 1.8 minus 1.2 is 0.6. So that's how much you've got. So 60 differences equals 0.6. So D equals, I'm just going to do it on a calculator, 0.6 divided by 60. 0.01 of a metre, so 1 centimetre. All right, 0.01 of a metre. Now, could you have done that another way? Could you have used a formula? I suppose so. So you've got to find T of n equals A n minus 1 times D. Now you know that this is 1.8. You know that this is 1.2, and you know this is n minus 1 times D, but you know that this n minus 1, because there's 61, sorry, T of 61, so we're finding T of 61, so this is 61 minus n. So you get 1.8 equals 1.2, and that's plus 60D. So you get, subtract that 1.2, you get 0.6 equals 60D, and you're right at that point there. All right, the second question. Assuming no wastage, that means there's no cut-offs or bits left out, what length of timber is needed for the fence altogether? Now remember, you've got 61 pieces of timber, you've got your A, you've got your D, you can just use S of n, but we're lucky because we know what the last one is. So we're going to use S of n, so here's B, S of n equals A plus L times D. We're going to use that other formula, that one, n on 2, sorry, n on 2. A plus L. What am I doing? Writing the wrong formula. So we know S of 61 is 61 on 2, 1.2 plus 1.8, which gives me 61 on 2 times 3. $91.5 meters. Let's just check that. And that's right. And look at that, we didn't even need D for that. You could have got away without using D for that. If you use this formula, however, you would have needed the D. But because you had the first and the last term and you knew this was 61, you didn't need it. Okay. So let's have a go at 10, because I've done this one many times before and it can prove a little bit difficult because there's two sort of questions here, two series they're going to give you. And I don't know how Margaret's done it or how they've done it with their work solutions, but we'll see. I'll just create a little bit of space here. And it's always good to draw a diagram. Okay, so in a game, children start at the point P where there's a pail or a bucket. They run, and all these apples are 3 metres apart. So they run, pick up an apple, run back. Run, pick up an apple, come back. Run, pick up an apple. Okay. So let's have a look at the first one. So 10A. And I'm going to split these into two different types of series. 10A. So how far do they have to run for the first apple? Oh, they have to run 3 metres. How far to the next one? Well, they run 6. How far to the next one? 9. So my A is 3, and my common difference is 3. Now, or I can think about this intuitively. Here's the first apple. Here's the second apple. Here's the third apple. Oh, so the 10th apple will be 10 times 3. So the K apple will be 3K. Or you can go T of K equals A plus N minus 1 times D. A is 3 plus K minus 1 times 3, which is 3 plus 3K minus 3, which is 3K. I much prefer this sort of reasoning, but the formula will get you there. Now this is where this question takes a bit of a turn. How far does a child run to get all K apples, including return trips? Well, I'm going to set up another series. I'm not going to try and use the same series. I'm not going to try and use the same series. So if they go there and back, they've travelled 6 for the first apple. If they go there and back, they've gone 6 and 6, they've gone 12. If they go there and back for the next one, they've gone 9 and 9, 18. Now, I don't know how they do this in the back or in their work solutions, but this is just how I did it. So there's the first, there's the second, there's the third. My A is 6, all right? Now, if they're going out to get the K apple, well, they're going to go 6 Ks. So to get to the K, you've got 6 Ks. Now I have to work out how far, so I have to add up, because they run 6, plus they run another 12, plus they run another 18. So I can do it 2 ways. I'm going to do this 2 ways. I can use this formula, S of n equals n on 2, a plus 2a, n minus 1 times d. And what am I finding? I'm finding how fast. I'm finding S of n is k on 2, because they're going out to get k apples, 2 times 6 plus n minus 1 times 6. K. So that gives me k on 2, 12 plus 6k minus 6 gives me k on 2, 6k plus 6, which will give me k, if I multiply that out, 3k plus 3. And if I take the 3 out, because this is the way they've got the answers in the back, I factorise out that 3k and k plus 1. I wouldn't have done it like that. I would have said, well, that's my A and that's my L. So S of n equals n on 2 A plus L. And I'm going out to get the K, so K, 6, K on 2, 6 plus 6K, which I can rewrite. I can divide that through. I'm going to get k, and I'm going to get 3 plus 3k. Take the 3 out and write it the other way around. Now, part C. If the child runs 270 metres to fetch all the apples and returns back to the bucket, how many apples are there? So how many apples have they got? Well, we've got to use this S of k, and we've just worked it out. So here's 10c. S of k equals 270, or S of n, and we've got, 3k, k plus 1 equals 270. Because we just worked that out. That's the sum of all the ones. Okay, so let's just divide the 3. K plus 1 equals 90. Let's expand this. K squared plus k equals 90. Bring the 90 over. K squared plus k minus 90 equals 0. So another quadratic. But this one's easy. I've got to find two numbers to multiply out to 90 and add up to 1. They're different in sign, so it's going to be k plus 10, k minus 9 equals 0. Therefore, k equals negative 10. Well, we ignore that negative. We ignore the negative. Or k equals 9. That means they've made 9 trips. So 9 trips, which means they've got 9 apples. Let's just check and make sure we're right. And indeed we are. So please don't lose sight of the fact that these are practical problems and you can use a practical or intuitive method to solve them, or you can just use a formula straight out. Please make sure that if you know the last term, you're going for this easy formula as opposed to this one over here, okay? If you know the first and last terms, go straight to that formula. It's much easier. All right, remember, email me if you're finding some of this difficult and you need some help.